board. Your learning journey starts now. Ever felt like math is just a bunch of rules handed down from on high? What if I told you there's a whole other world, a semantic one, where proofs aren't just about being right, but about understanding why and how? That's the playground we're diving into today with DMath Genesis Omega Infinity. So what is this proof world thing? A proof world is a living entity. It has its genesis, how it came to be, its relations, who it interacts with, and crucially, its purpose. Think of it like building a house. You need bricks, mortar, a blueprint, and a reason for building it. Genesis Omega Infinity uses encounters, typed relations, and counterfactuals, basically what-if scenarios to build these worlds. And completion? Not just ticking boxes, there are 14 non-compensatory gates. Fail one and no passing by fudging others. We've got solid evidence, not just hand-wavy arguments. Take the strong Goldbach conjecture. In this framework, it's considered semantically complete, grounded in its own world, not just because some old theorem couldn't prove it. Let's talk about those 14 gates. Imagine trying to get through airport security, but each checkpoint is critical. No single brilliant score can let you bypass a failed one. This is non-compensatory. Gate 1 fails, you don't just average out the rest. Each gate checks something fundamental. Is the purpose clear? Covenant. Do we have repeatable evidence? The encounter. Are the core relations sound? Are relations? Have we checked the counterfactuals? Counterwand. Across our 36 test cases, this protocol rigorously evaluates them. The result? A structured output, 144 detailed discovery proposals, 27 candidate hypotheses, and a queue of 144 specific research tasks ready to be tackled. It's about moving from vague ideas to concrete, testable steps. Now, what happens when things go wrong? When a proof world has a flaw? Enter counterworlds and repair. This system has an anti-self-sealing clause. If someone's a real contradiction or a counterexample involving the exact same object and purpose, the author's intention or the system's current state doesn't matter. The challenge is valid. The system must open a repair episode. It doesn't sweep it under the rug. It preserves the old state, analyzes the critique, reconstructs the problem area, and either branches off or revises the original. Then it reruns the audits. This isn't about avoiding failure, it's about learning from it. This process generated those 144 research tasks and 27 experiments we mentioned earlier, turning potential dead ends into new paths forward. So how does this engine actually find new stuff? It starts with problem genomes. Think of a problem not just as a question, but as a complex blueprint with all its components. We start with 36 of these. Then, using 27 reference experiments, we generate 36 initial proof worlds. From there, applying semantic mutations, we create 144 discovery proposals. These aren't just guesses, they're structured attempts. This narrows down to 27 candidate hypotheses, each needing rigorous testing, including kill tests designed to potentially disprove them. Finally, we get 144 falsifiable research tasks. Look at the top priority queue. Riemann hypothesis leads the pack. The point isn't just to churn out theorems, but to accelerate genuine mathematical discovery by providing concrete, testable targets. Why should you care? Because this changes how we think about math. It introduces semantic holonomy, meaning local charts, like traditional proofs, can be perfectly fine within their scope, but they don't automatically represent the whole truth of a Duan proof world. We are currently at evidence level E2, reproducible by the authors but not yet fully independent validation. The big takeaway? It offers a powerful new lens for tackling those stubborn open problems. The final step, claiming unbounded global closure, only happens with undeniable evidence, not just wishful thinking or semantic fluency. Math isn't static, it's evolving. Keep asking questions, keep exploring,